All right, so before we actually do anything in chapter 19, let's talk about where the semester is going to take us and where this next unit is going to take us. We talked about sampling distribution models for proportions and for means. We're going to be using that concept throughout the rest of the semester. I told you that. So our book breaks it down for you to begin with. So this unit, we're going to finish up some things. We're breaking it all down into pieces, and then we're going to start kind of putting it all together. We're going to be focusing on proportions for a while. So you can't just forget that means ever happened. We're just not going to be doing means for a while. We're talking about proportions specifically. Okay? So for proportions, we're going to talk about confidence intervals. Then we're going to talk about hypothesis testing. Then we're going to go into some more detail about hypothesis testing. Then we're going to start, every chapter is going to go into a different sort of sample, and we'll do confidence intervals and hypothesis testing for every different type of sample. Okay? So right now we're going to have it all spread out, but then eventually it'll all be condensed into the same chapter about the same type of sample, and so you'll be responsible for knowing how to do confidence intervals, how to do hypothesis tests. You'll be fine. But so once you do confidence intervals, they're not going away. At this point in the year, I expect you to know the things we're talking about and be able to translate that into the next chapter, right? So it's not like something we're going to learn something that's going to go away. It's not going away, not even a little bit, okay? So for chapter 19, we're going to need some things from chapter 18. So in general, in chapter 18, what do we learn about sampling distribution models for proportions? What do we need? What is it? How does the model work? Just the ones for proportions. So what are some things we learned? We have conditions, right? So there were some conditions we had to check. What else do we learn about the sampling distribution model for proportions? What was specific about it? What was the model? It was a normal model. What was the mean of it? That's not the mean. What's the mean? The mean. It's just P. What are the true population proportion is? Right? What's the standard deviation? Okay. So that stuff not going away. We're going to keep using those ideas. I'm going to reference that a lot today. Okay? All right. Now, you know how in our book, we always have some scenario that we have to talk about for the entire chapter, right? Always, every time. So this one actually, you have to, for any of this stuff to make sense, it uses the same thing the entire way through. So here's your setup, and you can go back and read the intro if you need to. That's fine. But they are talking about coral reefs, and they're talking about sea fans, which is a type of coral on coral reefs, and they're talking about them being infected with some disease. I don't remember the name of it, but some disease. They were looking for some specific disease. Okay? And so they talk about how there was this group of researchers, they go down to a specific reef, and they do a sample of 104 of the sea fans, which was not all of them. They did a random sample of 104 sea fans, and they figured out the percentage of sea fans that were infected with this disease. It ends up being like 51.9% or something. Right? That was the percentage or proportion of sea fans that were infected from this specific sample of a size of 104. All right? Now, here's the problem. With most real-life scenarios, I can't just do a sampling distribution model like we did in chapter 18 because I don't know the true proportion of sea fans that are infected with disease in all of the sea fans, right? I have no idea what it is. My 51.9% is a P hat. It's an estimate. It's something we came up with. So I don't actually know what P is. There's no way to know what P is, right? Sea fans live under the ocean, and there's thousands and millions of them, right? There's no possible, humanly possible way to go to every single coral reef on every single sea fan and figure out the proportion that's diseased. It's just not going to happen. That's not even practical. So I don't know what P is. I can't make a sampling distribution model like we did in chapter 18 because I wouldn't have a mean to the model, right? Okay, everyone with me? Okay, so we're going to kind of use that idea. Now, it talks about that if all of you, every single one of you, went to the exact same reef that the researchers did, yeah, and did a sample of 104 sea fans, again, it wasn't just there was 104 of them on the reef, they just did a random sample of 104. So if all of you went and did a random sample of 104 sea fans and figured out a proportion of the ones diseased, would all of you guys get the same number? No. And we call that sampling variability. Otherwise, we've called it sampling error. Not a bad thing. Sampling variability. Just that every single sample is going to be a little bit different. So how am I supposed to know if my sample is really close to the true proportion P, or if your sample is close to the true proportion P? We don't know. Like, we have no frame of reference. A lot of the time you have one sample and you have to use that somehow. So we have to be able to statistically explain the true proportion P somehow, or at least estimate it, or guess, or something. There's got to be something we can do. So we can think about taking all those different possible samples, but again, it's not practical. So it's easy to do a simulation of all those possible samples. And to do a simulation of all those possible samples, we're going to use those ideas from a sampling distribution model. We just have some issues. If we think about our sampling distribution model, do we have P? No. So that means we can't find the mean or the standard deviation. We do have P hat, though. So we're going to use P hat to make some estimates. Right? So you have to keep in mind that we're talking about estimates. So we're going to be talking about confidence intervals. Right? Generally, in a confidence interval, it's called a confidence interval because you have a level of confidence, 90%, 95, 97%, whatever. You're some level of confidence about your interval, and you're going to create an interval in which you think P exists based off your P hat. That's generally what that is, and we'll get more into that in a second. Since we have P hat, I said we're going to make some estimates. So you know that standard deviation formula that you have for the sampling distribution model for proportions? We're going to use that. We're just going to use P hat, so then we're going to also use Q hat. We have the sample size to find not the standard deviation, but we call it the standard error because it's an estimate. It's not the actual standard deviation. We don't know what P is, so we don't know what the actual standard deviation is. We do know what the standard error is because it's an estimate. Now, is that a formula on your AP Stats formula sheet? Not as it's written, but it is, right? In chapter 18, we talked about standard deviation being the square root of PQ divided by N. You just have to know now, okay, it's the same formula, really. We're just basing it off an estimate, right? So using our C-fans example, they come up with a standard error of 4.9%. Okay, no big deal. And so they know that the model should look something like this. If we knew P, right, then we have this standard error. So hopefully an estimate for one standard deviation above the mean would be here, and 2 standard deviations, and 3 standard deviations. Right? We're going to get there. We're just talking about it being, if we knew P, we have this estimate for standard deviation. We're just making sure we recall what that means. Okay? But we still can't do anything. There's no other numbers. Right? Can't do anything. So, if you think about 68, 95, 99.7 rule we've talked about and we've seen a million times this year, right? 68% being here, 95 I'm not going to do 99.7 because I don't really need it right now. So we know, looking at this model and looking at 95%, that for 95% of random samples, so if we had all of the possible random samples, that's what a sampling distribution model does, right? All of the possible sampling distribution models for size of 104, p hat will be no more than 2 standard errors away from p. That's what we've learned before. We got that. So if you talk about this being p hat, there's a 95% chance that p is no more than 2 standard errors away from your estimate p hat. Okay? So if I reach out on both sides of p hat, or p hat was 0.519, right? If you do 2 standard errors to both sides, then you're 95% sure that p will be within there. So you can have an estimate. You have this now have this interval where you think p might exist. Okay? So even if your interval catches p, we're still never going to know what p is. That's the whole purpose of this interval. We're trying to establish an interval so that we can try to capture where p would be. We're just never going to know what p is. So we're going to use our estimates to come up with an interval that we think p is going to fall in with a certain level of confidence. All right? So there's a little picture, help you kind of think it through. Yes. It's like your car salesman guy saying, here we go. So if you're thinking about p hat being your center, and you have plus or minus 2 standard errors, which is our estimate for standard deviation, on both sides, then we're talking about 95% confidence, so that's 68, 95, 99.7 rule, that we're going to trap p. So is it guaranteed that I track p? No. But 95% confident that we will, because 95% of the samples that we could simulate with that model fall within there. So we're 95% sure that p is going to be in there. Does that make sense? Does that concept make sense? Now, your confidence level, and we'll get into this tomorrow, does not have to be 95%. But we're going to use 95% today because it's easy, because it's 68, 95, 99.7. All right? You can be 99.7% confident. You can be 68% confident. You can be 90% confident. You can be 77% confident. You can be whatever confidence level you want. And we'll talk about how you figure that out tomorrow. Okay, so let's talk about that for a second. If you're 100% confident that something's going to occur, your interval then is from 0 to 100, because you're talking about proportions, right? If you're 100% confident that something's happening, then your interval is from 0% to 100%. Is that helpful in any way, shape, or form? No. That's why we're never 100% confident. Dang it. Stats never exact about anything. Okay. If we were 100% confident, that'd be great. It's right, 0 to 100 in every single question. Someone asked me in first period, they're like, well, it's not wrong. So could I just put that on the quiz and get it right? And the answer is no. You'll always be given a confidence level. Sorry. So if we get that concept, then let's go over some things that we can't say in conclusion. We haven't actually talked about getting an actual interval. We know plus or minus 2 standard errors, all right? But we need to make sure we can go through some conclusions and make sure we don't say the wrong things, all right? So here are 3 things that you can't say based on what I just told you. 51.9% of all sea fans on the reef are infected. That was our p hat. So does this statement make sense? No, it says all sea fans, right? That 51.9% is our sample. So I cannot guarantee that 51.9% is all sea fans. If you knew what p was, you could say that, right? We don't know what p was. We have an estimate. We have a p hat, so you can't say that. Got it? Because again, someone could do a different sample and get a different percentage. We don't know what p is. We can't say that applies to everybody. On number 2, it is probably true that 51.9% of all sea fans on the reef are infected. Again, this is almost the same thing as 1. You're trying to be more wishy-washy with probably. But again, 51.9% is a p-hat. Your sample could be a really wonky sample, right? It was just a sample. So everyone else in this room could have gotten a sample that had like 30 point something percent. 30.1 and 30.3 and 30.2 and 31.5. And your sample in the book here is 51.9%. So it's wonky, right? So I cannot say that it's probably true that 51.9% of all sea fans on the reef are infected. We don't even know if it's anywhere close to P. We have no idea. So we can't say that either. Does that make sense? And on the third one, we don't know exactly what proportion of sea fans on the reef is infected. But we know that it's within the interval 51.9% plus or minus 2 times 4.9%. All that says is this was p hat, right? This was plus or minus 2 standard errors. Remember the standard error was 4.9%. So it's just actually coming up with a percentage for you this time. That is, it's between 42.1% and 61.7%. Do we know that P is inside there? No. We're 95% confident that it's within there, but we do not know that it's in there. So yeah, you could say we don't know exactly what proportion of sea fans on the reef is infected, but we are 95% confident that it lies between 42.1% and 61.7%. But we do not know that P is in that interval. We can never be sure of that. Okay? Do those 3 things make sense about why you can't say them? Okay. So here's something, number 4 is what we could say, number 5 is what is better and what we should say. So 4 says, we don't know exactly what proportion of sea fans on the reef is infected, but the interval from 42.1% to 61.7% probably contains a true proportion. That's fine. That's okay. That's true. That's what we're going for. But what are we missing? 95%, right? That's got to come into play somehow. We based our entire interval off that percentage. That's our confidence level. So this is just kind of wishy-washy. It's kind of like, it could be better. Yes. Because we talked about an interval, so we're not really exactly sure anyway. And now we just say probably. That's why we want to have some level of confidence. Probably, does that mean you're 5% confident? Are you 35% confident? Like, what does probably mean? That's not a quantity. That's just a, Okay? So here's what you should say. We are 95% confident that between 42.1% and 61.7% of sea fans are infected. That's what a confidence interval is. All right? We have a level of confidence. That's always important in your statement. And we have an interval. So it's not a super long statement. But there are a lot of things that you can say that are wrong. So you got to be careful that you don't stray from what I'm telling you. Right. This is what's going to happen in the chapters we're getting ready to go into. Those of you that like to write stuff and make it a novel, the more you write generally, the more off base you're getting. You want it to be succinct because you want it to be to the point. When you start trying to explain extraneous stuff, then you get way off base and you're not going to get the score you think you're going to get on the AP exam.
So are we just assuming that, or are we just assuming that
Yes. So when we actually do, we're not going to do any math today. But when we actually build a confidence interval tomorrow, you're going to use your p-hat as like your center almost. And then you'll have a plus or minus that standard error on both sides so that you get that interval. But again, your plus or minus is going to come from how confident you are. And so it just kind of depends. You may or may not catch P, we don't know. So that's why we have a confidence level. Okay? All right, so also from now on, pretty much everything we do is going to have a name. And it would be helpful if you knew those names, so on the AP exam, you sound really good. These names are not fancy. This kind of confidence interval that we're talking about in this chapter is a one proportion, because we're talking about one proportion. In chapter 22, you're right, we're going to talk about the difference between two different proportions. They're comparing them. So then we'll have two proportions, but we're talking about one proportion right now. It's called a Z. What does Z relate to? Z-scores, which relate to what? Yes, you do. There's standard deviations for a normal model. So Z indicates we're using a normal model, sort of. And it's an interval. Like, that is not a fancy name. We got a one proportion Z interval. Okay? Not fancy. All right. So we're going to do the just checking from your book real fast. And we're going to talk about some statements, if they are correct or not. Okay? We're going to practice what we just talked about. See if you can put it in a different context besides the C fans. All right. A Pew Research study regarding cell phones asked questions about cell phone experience. One growing concern is unsolicited advertising in the form of text messages. Pew asked cell phone owners, have you ever received unsolicited text messages on your cell phone from advertisers? And 17% reported that they had. What is that 17%? P hat. That's an estimate that you came up with of one sample, right? Pew estimates a 95% confidence interval to be 0.17, again, that's your p hat, plus or minus 0.04. That's going to be your standard error, right? That's going to be 2 times your standard error, because it says 95%, right? Okay. Okay, so, or between, and it gives you the decimal, the percentages, sorry, 13% and 21%. Okay? So we know what p hat is. We know 95% confidence, so we know the level, and we also have the interval. So here are a lot of things that they're saying. We decide if any of them are correct and explain why or why not. Okay, in one. In Pew's sample, somewhere between 13% and 21% of respondents reported that they had received unsolicited advertising text messages. Okay. Right. This is technically a correct statement, but we know it's 17%. It says respondents reported. Yeah, 17% did. So, like, is that a confidence interval statement? No. Like, that is not, like, there's no reason to make that statement. We know that 17% responded that way. Yeah, so it's technically correct, but there's just no reason to say that. Like, what are you going to say that for? We know it's 17.
But if you just said, that you would just say,
If it wasn't about this sample, it would still need some extra information. It's missing the confidence piece. So yeah, one is technically a true, correct statement, but it's a stupid statement since we know it's 17%. Technically. On number 2, we can be 95% confident that 17% of U.S. cell phone owners have received unsolicited advertising text messages. That's false. We are not 95% confident that our P is P hat. That's wrong. I think everyone can say that's wrong, right? Okay. On 3, we are 95% confident that between 13 and 21% of all U.S. cell phone owners have received unsolicited advertising text messages. That is true. That's what we want. 95% confidence that all U.S. cell phone owners fall in this interval, right? The true P falls in there. Okay. On 4, we know that between 13% and 21% of all U.S. cell phone owners have received unsolicited advertising text messages. False. We do not know. We're 95% confident that it's in there somewhere. We do not know. Again, this is based on one sample from one day. And then number 5, 95% of all U.S. cell phone owners have received unsolicited advertising text messages. That has nothing to do with anything, right? Talk about 95% confidence. That does not mean 95% of people. Now, because it's based on a sampling distribution model, 95% of samples should include the true proportion. But I don't even think that's what they were going for here. I think they were just like way off base. Okay? All right. So let's kind of make sure. I'm going to circle back. I've got 2 more slides and we'll do some examples. I'm going to circle back. This might get repetitive. I just want to make sure I really understand the concept of confidence interval. Okay? So what does 95% confidence really mean? 95% of samples of this size will produce confidence intervals that capture the true proportion. Because it's all based off of a sampling distribution model, right? A sampling distribution model is a simulation of all possible samples of that size. This is correct but a little long-winded, so we sometimes say we are 95% confident that the true proportion lies in our interval. And I'm totally okay with you saying that. But make sure you know that the first statement's not wrong. Our uncertainty is about whether the particular sample we have at hand is one of the successful ones or one of the 5% that fail to produce an interval that captures the true value, right? If we're 95% confident we've trapped P, well, that means there's 5% of samples that didn't trap P. All right, that's why we're not 100% confident. So here is a good illustration. The orange dots are all different samples. We'll say it's for the C fans, okay? They're all different samples. It's like all of you went into the ocean and took a sample, and you came up with your proportion. It was your orange dot. Got it? So that's your infected C fans. Then you came up with your confidence interval, which we haven't really talked about how to do that yet, but let's say you knew how to do it. And you did plus or minus 2 standard errors, okay? So the blue bars represent the actual interval. So you can see they're all a little bit different based on where the orange dot was to begin with, right? And then the green line, let's say they somehow figured out what P was. The green line is where P is. So you can see that some of these don't capture P, like this one doesn't cross the green line. So it didn't actually capture P. So it was one of those kind of bad samples, right? This one doesn't capture P. This one doesn't capture P, right? That's why, again, we're only 95% confident, because it could be that we don't actually capture P in our interval. And that's okay. We know that going into it. So this is what's important to take out of this. Every single sample has a different confidence interval. So all of you guys could go out there and get different percentages to start with, which makes your standard error different, which makes all of your intervals different. Okay? So every sample has a different confidence interval. And so you never know if yours is actually going to work. That's why we're only 95% confident. We're never certain. Let me throw in one more vocabulary piece. It's not that difficult. We have the margin of error. All right? In general, the ones we've been talking about have this confidence interval. We have P hat plus or minus. We've been talking about 2 standard errors today, right? All right. So this part right here, the interval on either side, is called the margin of error. So all confidence intervals, no matter what kind you're doing, you have an estimate plus or minus your margin of error. Your margin of error is just going to be different for every different type of thing we do. All right. In this case, we're doing proportions, so it's that standard error we talked about already. Okay? Now, this is why this is important. The margin of error for a 95% confidence interval is 2 standard errors. But we could be more confident if we wanted to be. To be more confident, we need to capture P more often, and to do that, we'll need to make the interval wider. So for example, if we want to be 99.7% confident, the margin of error will have to be 3 standard errors, right? Using that 68, 95, 99.7 rule, right? So here are some things you need to take away from this. To be more confident makes your interval wider. When you make your interval wider, you become less precise, right? Let's say you want to do the opposite. You want to make your interval more precise. So you make the interval smaller. That means that you have made it more precise, but you have less confidence, so you're less certain, right? So it's kind of like this give and take. If you change something, you're going to change one of those levels. How certain are you? How precise are you? Right? How confident are you that's in here? And this interval's wide, or this interval's small, but I'm not that confident about it. Okay, so that's why a lot of the times you'll see confidence intervals in like the 90 percentages. Because you want to be fairly confident to make it mean anything. Okay? So the more confident we want to be, the larger the margin of error must be, and there's the things I just said. The more confident you are, less precise, more precise, less confident. I think that makes sense if you picture that in your head, right? All right, we're going to do 2 quick examples, and then you have 2 homework problems. They're just like the things we've been talking about already today, so they're not anything fancy or tricky. All right, number 1. A TV newscaster reports the results of a poll of voters and then says the margin of error is plus or minus 4%. Explain carefully what that means. So we have plus or minus 4%. So what else did they probably have at some point along the way? They had a p-hat. They had some sort of sample, right? And they had plus or minus 4%. Then what are they trying to tell their audience? They're trying to tell them, they don't give me a confidence level on this question, but they're trying to tell them that hopefully the true proportion of voters voting on whatever, because they're being very vague in this question, right, is within 4% of their sample, right? So using that confidence interval idea, that's how you do explain it. That the true proportion of voters voting for blank, since it doesn't tell us, is within 4% of their sample. All right. Then let's do 5. And 5 talks about conclusions again, correct statements, false statements. And I'll give the assignment. A catalog sales company promises to deliver orders placed on the internet within 3 days. Follow-up calls to a few randomly selected customers show that a 95% confidence interval for the proportion of all orders that arrive on time is 88% plus or minus 6%. So 88% is our p-hat, right? And then plus or minus 6%, that's our margin of error. So what does this mean, and are these conclusions correct? So we're just looking at these conclusions and saying why or why not. Yes, they're true. No, they're not. The margin of error is just a general term for however many standard errors you are above or below the mean. Okay. All right, so on A, between 82% and 94% of all orders arrive on time. False, because, yeah, this is way too definite, and there's no level of confidence. On B, 95% of all random samples of customers will show that 88% of orders arrive on time. False. 95% of all random samples of customers will show that, yeah, they're just going to show that, yeah, they're going to hopefully lie between that interval, and your true P is going to be in there somewhere. It does not say that it's going to be exactly 88. Every sample is different. On C, 95% of all random samples of customers will show that 82% to 94% of orders arrive on time. That's not true technically. Again, 95% of samples, we're not talking about samples. We're trying to talk about the true proportion, right? 95% of samples should catch what P is, but 95% of samples don't have to have the same interval that I have, right? Again, if all of you guys had a different sample, you would all have a different interval. So here they're still talking about samples. We're trying to get to like the true population here. We're trying to get somewhere else. So on D, we are 95% sure that between 82% and 94% of the orders placed by the sampled customers arrive on time. That's one of those that's technically true, but you're really 100% sure because 88% are the ones you polled. 88% said their stuff arrived on time. Right? This is still talking about sampled customers. It's not talking about the population as a whole. And then on E, on 95% of the days, between 82% and 94% of the orders will arrive on time. Yeah, that's nothing to do with days. What is the correct statement we should make here?
Most correct?
Yeah, what is a correct statement we could make? Now, what is the one that we could make? I am 95% confident that the true proportion, P, of orders that arrive on time is between 82% and 94%. That's the statement you should make, right? All right.